Now this is the most important thing I'm going to say the whole time. The first thing I'm going to tell you is to forget everything you heard in the previous talk.
What?
Forget everything you heard in the previous talk except the small bits of information that I'm going to tell you now, which I will continually use. So either you know where they come from and there's a vast, enormous, gigantic Grothendieck theory behind them, or you don't, and it doesn't matter. These are the things we're going to use. So for all Q, variety, quasi-variety, scheme, stack, if anyone likes it, whatever, X, there is a canonical outer action of the absolute Galois group on the algebraic pi1, which is the topological pi1 profinite completion. I'm going to say a couple of words about this. I'm going to tell you why this is true in a really, really simple way that doesn't, of course, give the big picture that you got in the previous talk. But you think of your variety, X, just some variety that happens to be defined over Q, but you can just as well define it over C, and you take its function field. And here, well, here's X, and here's the universal cover of X, but that's not really a variety, so we can't just like take its function field over here. But between them, there's a whole bunch of covers. And what you do when you look at this function field situation is you only look at the finite covers. So they're all quotients. So here's the topological pi1. And here's all these finite covers that correspond to finite index subgroups of the topological pi1. That's the Galois correspondence, the geometric Galois correspondence. And here you have C of y, but that's a finite group. And here you have like the compositum of all these C of y's put together, all of them. And what's the Galois group of that? So all the C of y's. Composite of a big field. But it's not, in any sense, a function field of the universal cover. It's what you get when you put all the finite covers together. And the Galois group here of these fields has all the same finite quotients as pi1. That's how it's defined. It's got all the same finite quotients as pi1. And it's nothing other than the inverse limit, because they form a compatible system, all these finite quotients, of the finite quotients of the pi1. And that is the profinite completion. So the profinite completion is something that comes up completely naturally when you move from your X to function fields and you think only of finite covers. Now, why is there a Galois action on this? Simply, you can first move to Q bar. So there's just a standard Lefschetz theorem that says if I have an algebraically closed field inside my algebraically closed field, the same Galois group will remain if I go down to the scalars Q bar. This is the big compositum of all the QY's for all finite Y's. So I keep the same Galois group. That's a fundamental Lefschetz theorem. But now I have under here, so this is what we did here in the first talk. My variety is defined over Q, so it makes perfect sense to take functions over Q. And so now I have another field extension, and nothing happens here except that coefficients are moved by the Galois group. So the Galois group of this is GQ. And this just really simply explains why you have a outer action of the Galois group on the profinite fundamental group. And I'm going to say the semi-direct product. The whole thing from all the way up here, all the way to down here, is not always a semi-direct product, but as we heard in the previous talk, it is a semi-direct product whenever your variety has a rational point. And that's always the case that will be in here. So we will always be looking at semi-direct products. I call this the arithmetic pi1. Okay, so this, I will be using it all the time, so keep this one in mind from what you heard from this morning. And this is, establishing all of this is one of the fundamental purposes of SGA1. And I'm going to say one second really important thing, which is, basically this is all we're going to need from this morning. So you really don't have to come to this talk. You know everything and more than everything. Are you sure? Okay, in fact, he has actually done some of this. Okay, so waste of time for you. There's something very important about this action on the pi1. GQ has, well, it's outer automorphisms, but this could be some really simple group like we saw this morning. When x is p1 minus 3 points, this is the free group on 2 generators, tons of automorphisms. Which ones are Galois? This is the big question that Grothendieck wanted to look at. Exactly this. Which ones are Galois? And the first thing he wanted to look at was in the case of F2, and then more general cases that we're going to look at. And one thing you can say is Galois has a very special property when it acts on these. It has a very special property, which is that it preserves inertia. So I'm going to talk about inertia for a sec in two different ways. First, the inertia groups are, there aren't always inertia groups, but when they're there, here it's the standard definition of inertia groups for fields. But I want to talk about what inertia groups mean in the geometry, so with respect to the variety Q. So if your variety is a quasi-variety, if you have, okay, let's talk about a compactification of the variety. You have a compactification of your variety. This compactification is obtained from the variety by adding divisors at infinity. And in your space, you have loops, certain loops, which go around these divisors, but they're actually in your space, and they go around the divisors that you added at infinity. Those are the inertia generators. I prefer to talk about them that way because that's how we're going to see them in all the examples that we're going to be working with. So in the special particular case that we always like to start with, the inertia generators are the XYZ that we saw in the previous talk, just loops around these three missing points. So here the inertia, the divisors that you'd add to compactify are the 3 points, 0 and infinity, put them back. And the loops around them are the X, the Y, and the third one Z, so that the XYZ equals 1. Those are the inertia generators of the pi1. And GQ preserves inertia. This is such a fundamental property of the Galois action.
What do you mean by preserving inertia?
So what I mean by preserves inertia is that we have cyclic inertia groups. So if X, let me say gamma, is an inertia group, then...
So what's an inertia group? Yeah.
Okay, so what I just told you was, it's generated, they're cyclic. We're dealing in a situation where they're always going to be cyclic. They're generated by a gamma, which is a loop surrounding a divisor at infinity, by which I mean a divisor that you add in the compactification of your space that you're working with. So gamma is one of these loops I was just telling you about, like the loops.
Just the group generated by...
Just the group generated by gamma, cyclic group, cyclic inertia groups. Then sigma in the Galois group, what's it going to do to gamma? It's just going to take it to a power of gamma conjugated by some element of the group. This is what I mean by preserves inertia. Or if I put the group here, what it really preserves is it preserves conjugacy classes of the inertia group, which is exactly what's being said here.
Isn't everything wrong? Isn't everything's a loop around something kind of?
No. XY is no.
I see what you mean.
Just one simple closed loop around a divisor in infinity, okay? Now, if I were to express what Grothendieck was thinking when he wrote the Esquisse-Tempogram, which I meant to bring and read you some of, but I forgot, was, is there any way, could we dream that this property suffices to define, to find the Galois image inside here? Well, certainly not if pi1 is too simple. If pi1 is abelian or something, that's never going to work. You want a pi1 complicated enough for this to be an injection, and you want a pi1 complicated enough for the automorphism group not to be gigantic. So F2, for instance, would not work. But he wanted to look at more complicated pi1s, which we're going to do very soon. But the question is, I write star here for just this condition of inertia preserving. Could it be that these are equal? for a sufficiently complicated X, even for any given X. So is there something? Can you get the Galois group back this way? And if you could, you'd have a completely different description of GQ, because you write down all the automorphisms of this group that are inertia preserving, and that gives you a completely different description of GQ. So what Grothendieck suggested doing, and what was completed, at least in genus 0, by the work of Drinfeld and Ihara did more in the Lie algebra situation. I'll be getting to that quite a lot in the next week, but not today. What he did was to choose certain x's, which are moduli spaces of curves that I'm going to talk about, and to calculate these groups, and to show that you can actually calculate them. You can write down who they are. Not by generators and relations. It's not a presentation, but it is a complete description. And then you can ask yourself the question of whether GQ does have, well, first of all, you know there's an injection into these groups, and then you can ask yourself whether there's equality. The groups I'm going to talk about are these groups for certain pi1s of certain x's, the genus 0 moduli spaces of curves, and that's what we're going to be calling the Grothendieck-Teichmüller group. Okay, so my goal now, I'm going to leave GQ until the end. Now I'm going to leave arithmetic, and I'm just going to define GT and tell you some interesting properties of this group GT, the Grothendieck-Teichmüller group.
So this works for in X, this works for any Q variety X, and then you're going to take the simplest examples.
I'm going to take the example P1 minus 3 points, and then I'm going to take moduli spaces of genus 0 curves, which are very simple. They may not be the world's simplest example, but they're great, and they're not that hard to talk about. In genus 0, they get worse in higher genus, but we'll get to that in a couple of weeks. Okay, so my first goal is to define braid groups, Artin braid groups, really, moduli spaces in genus 0, especially in genus 0. I'm going to give the definition in general, but I'll describe them in genus 0. We're going to move to higher genus later, but today genus 0. They're pi1s. And then that will just be the background I need to define GT, the Grothendieck-Teichmüller group. So keep in mind at all times that what I'm aiming for is that this group is an outstar of pi1 of these varieties. Therefore, GQ does inject into it. And it may even be a description of GQ. And this is the point. Some properties. 3, discuss. Prove. I may not prove everything completely, depends on the time, but this injection, how we know it, what it is, how explicit it is. Okay, so that's basically the idea for today. Before I get to the definition of GT, I need this background, so I'm going to start on this background now. So let me remind you of the definition of Artin braid groups. I'll give it to you in 2 ways. I don't want to bog down into defining a bunch of objects without this remaining clear that the goal of today's talk is to do this. And the goal of the whole of Grothendieck-Teichmüller theory in general is to capture, I'm going to say, a profinite group that could possibly be a description of GQ. And then in any case, since there's an injection, does contain a lot of elements of description of GQ, and to study this mysterious group from that angle. This is the point. And then secondarily, you can study, you can take all these other avatars of GT that we heard about this morning. So there's a pro-unipotent version, there's a Lie algebra version, there's a, well, essentially those are the names, there's a nilpotent version, there's a pro-L version. And all of them have some kind of Galois correspondence as well, where it isn't the full, amazing, absolute Galois group that comes into play, but some smaller thing connected to it. But this is something that happens on many levels. And what is interesting is that although this, we don't know at all here how to prove that it's an isomorphism or whether that's even true, there's a lot more hope of doing it on some of the lower levels, like when you get down to the Lie algebra level. Well, there's progress in that direction for sure. It's not done, but it's something that looks much more doable. So it gives less information than the full Galois group, but still, it's like something smaller associated to it. So at all times, the goal of this theory is to get a different description of the Galois group or these other avatars of the Galois group. Because we want to know what GQ looks like, so nobody does. Okay, so that has to be kept in mind while I go into all the necessary definitions of things. Okay, so I'll give you two definitions of this. One is just generators and relations. So for each n greater than or equal to 2, even 1 if you want a cyclic group. No, 2, and it will be cyclic, okay. So you have n minus 1 generators. And the relations are only these. Sigma I commutes with sigma j if j and I are not right next to each other. And if they are right next to each other, sigma I and sigma I plus 1 satisfy a famous braid relation. Okay, so the way to understand these groups is you take a bunch of strings. I take a bunch of strings and hang them from the ceiling. I often actually do this. I have strings in my office and I often braid them because whenever you have to prove some really complicated identity that turns up in braid groups, you just braid it. You don't bother with the calculations. Much easier. Sometimes I'm using the phone cords and electricity. Okay, so this is sigma I, let's say. This is sigma I. And the relation, you can see right away. I'll just do the relation here. Sigma I plus 1, sigma I again. And if I do it the other way, first, so this is first I, then I plus 1, then I. Now I do first I plus 1, then I, and then I plus 1. And all it is the two guys here cross, and the guy in the front passes in front of them. And if you think of real strings, it's exactly the same thing homotomically. It's just the same thing. So it's just actual stringy braids with the homotopy that you get when you're actually braiding braids. The only thing about these strings is you can only braid them downwards. You don't have, they can't go back up again. Like if you tie a regular granny knot, that's not a braid. That's a tangle. There's a more complicated theory that deals with that. Can't do a regular granny knot going all the way down. Okay, so now I'll talk about the moduli spaces in genus 0. And the reason is that these braid groups are very close to their pi 1s, and that's why we're going to be using them. Okay, let M0n be the moduli space of genus 0 curves, which just means Riemann spheres, right? There's not very many genus 0 curves, with n ordered marked points. So what the moduli space means is that every point of this moduli space corresponds to an isomorphism class of these things, of these spheres. So what's an isomorphism class of spheres with n marked points? So an isomorphism class of P1 minus x1 xn. Well, what are the isomorphisms of a sphere, the automorphisms of a sphere? It's just PSL2 of C. These are the automorphisms of a sphere. But if I have marked points, my automorphism has to move these points to some other points. And I want to tell which are the points in my automorphism class. And it's very easy. These are 2 by 2 matrices, and any 3 points I have, there's a unique element of this that will send them to any 3 points I want. Because it's a 2 by 2 matrix. You just solve the equations. So what I always do is I send them to 0, 1, infinity. It's really just a way of picking a representative. This is always equal by somebody in PSL2 of C to P1 minus 0, 1, infinity, tau 1, tau n minus 3. This is what I take to be a good representative of the isomorphism class. So all I really need to do is take these n minus 3 points. So in fact, the moduli space, M0n, is really not much more than P1 to the n minus 3. Except I have to be careful because the points are distinct. When I say n points, I really mean n points. So I'm going to just take out the things that make them equal. So my tau i's have to be different from 0, 1, and infinity. And they have to be different from each other. So I take off this big diagonal, which is all tau I equals tau j. I take out all those lines, okay? So that's my moduli space. And every n minus 3 tuple of points simply means this sphere, which is in the isomorphism classes of all the spheres you get by doing parallel to the. Okay? Now, suppose I told you that the pi1 of these moduli spaces is very close to the braid group. Just modulo something. A couple of simple relations which I'll tell you what they are. But first I want you to visualize this. All the time that we're doing these lectures, except when I'm talking about Lie algebras, all the time we're doing the geometric parts of the lectures, I always want to think of the elements of the pi1 as paths. The elements of the categories as paths, the associativity moves as paths, everything, the braided tensor category as paths. I like paths. So, of course, when things are profinite, it becomes difficult. So how do you have a profinite path? Well, you have a profinite path. You have all the finite covers, and you have a path that lifts your path all the way up, and it's a compatible system. You have a profinite path. I like paths. I just think they're visual. So you have a sphere, Pierre. T'as pas trop besoin de rester, vraiment. J'ai déjà renvoyé Photoshop. J'ai déjà renvoyé Photoshop. Okay, you have a sphere with n marked points. And it is sitting somewhere in your moduli space. So let it be your base point for, I'm going to talk about the base. I'm going to talk about a path on a loop on your moduli space. An element of the pi1 based at this point, which is a sphere with n marked points. And what does it mean that you have a path on moduli space? Well, if you draw a path on moduli space, your path passes through all these points. And these points are all spheres with n marked points that are gotten continuously from the one you started with just by moving the points around. So what you want to think of is, well, it's nice to think of it in time. If you take your sphere and you have these endpoints and you let the sphere grow with time and the endpoints are moving around the sphere, but if you draw them all on the sphere, they cross. The condition is that if you draw it, out growing in time and they're all crossing each other, they're all moving around, they can never cross if you put it in the three-dimensional picture, okay? And these are the braids. These are exactly the braids. It's all these points moving and going through time are forming these strings which never cross. So you can really right away see why the pi1 is braids, except that before the braids I defined where you were hanging from the ceiling, and now they're hanging from a sphere, and you can go around the back with the braids, and so there's a couple of little relations. But these are not very important. I'll just tell you what they are. First of all, the braid group has a center, and the center is the product of all the n's, the sigmas to the n. And it just consists in taking this and like a ribbon, like if it was some flat thing, and doing a complete twist on it. If you do that on a sphere, if you do that on the ones on the ceiling, it's non-trivial, but if you do it on a sphere, you can undo it by taking the first guy and bringing it all the way around, And that is, on the sphere, it comes back to itself, it's trivial. And then you take the second one, go all around, the third one.
You take the pure braid group or the braid group?
I'm now taking the, let me just introduce the moduli spaces of spheres with unordered points, just by quotienting by the action of S and permuting the points. I'll take both, actually. So the one I'm doing now is the one with unordered points. Okay, this thing of taking a thread and taking it all the way around and bringing it back is trivial on the sphere, and you can write that this way.
Is there a shift between the n? I mean, you take n and then n minus 3 points, or is there a shift between the n? Is it bn minus 3 now on the right hand side?
No. It's bn because when you draw a path on moduli space, all the points move.
But then you have PSL2 active, so they are
Okay, let me just finish this, and then we'll do just M04 and M05. Okay, we'll just look at those. I just wanted to. Well, this is the relation that goes in there. Okay. Okay, so that just means that your braids are growing on a sphere instead of growing on a plane. I'll leave that one. Okay, let's do the first cases. Let's do n equals 4, okay? The moduli space M03 is just 1 point because it's just P1 minus 0, 1, infinity. They're all P1s with 3 bar points are equal to this one we just saw, so it's just a 1 point space, but it's no pi1, so it's not interesting. So let's look at M04. And we're going to look at M0 bracket 4. Okay, so what is this? So we know what it is. It's P1 minus 0, 1, and infinity to the power n minus 3, which is now 1. So it is P1 minus 0, 1, and infinity. And so let me draw a picture of it. Okay? And this is the same thing, mod. Okay, this just a little thing happens here that's complicated, which is the following. I should write S4 by the definition, right? And I can write S4, but this is cute. The actions of 2 permutations, they fix the points of M04. For instance, if I take 0, 1, infinity, tau, and I act on it with this permutation, I get 1, 0, tau, infinity. And then if I do a matrix in PSL2 of Z, I could get these back to 0, 1, infinity, and I find here tau. This one is actually fixed. You can do this exercise if you feel like it. You just have to find a matrix AZ plus B over CZ plus D that takes this to 0, this to 1, and that to infinity. So something's going to be like 1 minus Z. Well, I won't write it down. Okay, so in this case, S4 does not react faithfully. So I'm cheating a little bit. I can do this. I can do just quotient by the quotient of S4 by the Klein 4 group. So this is well known. What do I do when I mod this out by S3? This has to do with elliptic curves. What I get is, okay, I get a fundamental domain. They are divided into 6 pieces, and the fundamental domain is just 1/6 of it, and that gets sewn together when I do the quotient by the automorphism, and I get a thing like this. This is actually, you can see this as being the J invariant. You can see this is parametrizing elliptic curves, y squared equals x, x minus 1, x minus lambda. And this map being the J invariant of those elliptic curves, which is the same J invariant for 6 different values of lambda. And in fact, this goes back to something we saw in the previous talk. The 6 values of lambda that have the same J invariant are the 6 values of lambda under the group S3 that we saw this morning, that's generated by 1 minus z and 1 over 1 minus z. That gives a little S3 of things acting on C. And it usually has 6 different images. There's some ramification points here. The dots are ramification points, and then it has 3 ramification points. But it's also a P1. It's almost a P1 minus 3 points. I mean, it's a P1 with minus 1 point at infinity and 3 funny points, and 2 funny points. And it's the fundamental domain for elliptic curves. Okay, so what's the pi1 of that? The pi1 of this is just F2. The pi1 of this is PSL2 of Z. I won't say SL2 of Z. I could say SL2 of Z, but I'll keep it simple. Okay. So now I'm going to, I told you before that it was B.
So sorry, why the pi1 of this is PSL2Z?
Why the pi1 of this is PSL2Z? Well, because this is, okay. You have to study the ramification to calculate what it is. You have to study the ramification of this map. The ramification of this map, I won't write down the rational function, but it's a very well-known map. 3 points have ramification of order 2. 2 points have ramification of order 3. And therefore, the pi1 of this is freely generated by an element of order 2 and an element of order 3.
So what's the general statement about maps and ramification in pi1? Or how do you get this computation?
well, you take the fundamental group of this one up, and this is the quotient of it, and this is the Galois group S3, and you have a short exact sequence. This one you know it's F2. Here you have the group that the big one. Here you have S3. And here you have the pi1 of the quotient. In general, you can always do this. If you have some topological thing and a finite order automorphism acting on it, or a finite order group of automorphisms acting on it, you can calculate the shape of the quotient with a ramification. This isn't exactly a variety. This is an orbifold. Okay, this is a manifold, but this one is what we call an orbifold, and I'll tell you what we mean by an orbifold. An orbifold is almost like a manifold. It has a universal cover and a pi1, just like a manifold, except that whereas for a manifold the universal cover acts freely, properly, discontinuously, when you have an orbifold, what that means is you have a group acting properly, discontinuously, but not freely. You have fixed points. And those fixed points, they come down and they make ramification points here. Okay? And that's going to be happening. We're going to see this all the time. We're actually, what I told you before, when I said you always have an action of the Galois group on a pi1, it's going to be, when I wrote stacks up there, but if you forget the arithmetic of it, if you think topologically, those are orbifolds. Almost all the moduli spaces we're going to look at, they're going to be like this. They're going to be orbifolds, which simply means that the pi1 acts non-freely on the Teichmüller space, really, which is the universal cover. But in all the situations that we ever have, the pi1 acts, there are fixed points, but only fixed by finite subgroups. It's a very easy case to look at. It's very particular what happens. And the finite subgroups at fixed points are exactly automorphism groups of the curve corresponding to that point. Okay, so we know we have an elliptic curve that has a special automorphism group. There's a Z mod 4Z, and we know we have one that has a special automorphism group, Z mod 6Z. Okay, I'm fudging a little bit here, because if I should put S4 here, and I should put SL2Z here, but I like to ignore the fact that this acts trivially and forget it. Well, you're not really supposed to forget it. If you want to talk about elliptic curves, you have to keep it. This group is freely generated by an element of order 4 and element of order 6, corresponding to the two elliptic curves that are special. Okay, but what about the braid groups? What about the braid groups? Okay, so I am going to tell you that. Let me go back to PSL2Z and not worry about the special structure that every elliptic curve has an involution. So PSL2Z is equal to the braid group B3 mod center. So what did I tell you? I said that this was the pi1 of M04. Okay, so it's n minus 1. However, now I'm going to talk to you about pure braid groups. So something interesting happens with the pure braid groups. Okay, pure braid groups. So I'm going to write Kn is the kernel of the map Bn to Sn. These are the permutations, where this is just looking at what happens to the ends of the braids. So I braid, and the first braid goes to some position, the second braid goes to some position, that's a permutation. And I look at the kernel. So I'm looking at braids where the ith strand braids around and it goes back to the ith place at the end. These are pure braids. I'm going to write gamma 0n for the pi1 of M0n, and gamma 0n for the pi1 of M0n. And now I'm going to say, but I'm not going to prove this because it's just a little bit of group theory calculations. Gamma 0n belongs to Bn minus 1 mod center. Because actually, somehow you can create this group with, you don't need the generators that actually involve the last strand. If you don't take those, you still generate the whole pure group. So even though this is B3, F2 is equal to F2K4. That's interesting. F2 is equal to, let me do this completely. I'm just going to show it to you with sigma 1 and sigma 2. I will be clearer that way. Let me just actually take the generators, and I'm going to tell you exactly who they are.
So didn't you want to use Kn instead of Bn there? You wrote gamma 0n. So
Yeah, so the pure on n strands mod those relations,
It is Bn.
yes, belongs to the non-pure with one less strand, mod the center. Which is why it's turned out the PSL2 is B3 instead of being B4. Okay, I'm going to show you this. I think it will be simpler if I do this. I'm just going to do it for P1 minus 3 points. Okay, so
N minus 1.
I'm going to call this path, I'm going to take the tangential base points. Oh, I forgot to say that the other thing you have to keep in mind is that we're going to use tangential base points. But for now, I'm going to consider a tangential base point topologically, which means just a simply connected little thing. Later, I have to have some arithmetic. But now, all you're going to think of is the pi1 is the same if I take a point or if I take a simply connected region as my base point. Same pi1. Okay? So I'm going to let my base points be simply connected region, and I'm going to take this simply connected region right here on the real axis. And this one and the other ones, but I'm only going to need this one. This will be my base point, this one here. That's what he was calling a tangent vector this morning when he was saying it's the direction that your curve goes in. I'm actually going to take this little region. And I'm going to take this one. And this path, I'll call it sigma 1. And this path, I'm going to call it sigma 2. Now, if I take P1 minus 3 points, mod the action of S3, these become loops. Because these points, all 6 points are, there's 2 more tangential base points around infinity here. All 6 of them are identified under the cover, the degree 6 cover. And these paths become loops. And they generate the pi1. So sigma 1, sigma 2 generate pi1 of M04. And the relation is this. And that's the only relation. No, we have another relation. We have mod the center, which is over there. And this is the braid group. This is PSL2 of this is PSL2, which is freely generated by an element of order 2 and an element of order 3. And the reason is, well, here's your element of order 3, and here is an element of order 2. This is equal to 1, simply because if I write sigma 1, sigma 2, sigma 1 times sigma 1, sigma 2, sigma 1, and I use this relation, this becomes 2, 1, 2, and it becomes sigma 1, sigma 2 cubed, which was part of my original relation. So these two relations are equivalent to these two relations.
Sorry, could you say again how you view sigma 1 and sigma 2 into pi1 and M04? You use the covering you were talking about?
I do it on P1 minus 3 points, so they're not loops. But yes, I use the covering. When I quotient, all 6 base points become 1.
Can you recall what was the covering?
Okay, so okay, let me draw it this way. This is P1 minus 3 points. And when I do the covering, I have some ramification points which are the 6 roots of unity, actually. Now, I've cut my P1 minus 3 points into 6 pieces doing this. And this is a fundamental domain, one of them. One of these triangles is a fundamental domain for the action. And when I quotient, I sew the edges together. So I sew this to this. And this one gets folded in 2. Okay, so what I get is, but this is a pillow. I mean, it's a sphere, but it's pinched. It's got these pinched points with a hole at the top where this is a hole. Okay, these are ramification points of the cover. Okay, so there's a ramification point of order 2 and there's one of order 3. And What was your question exactly? What happens to a loop that does this? Ah, that's your question. What happens to a loop that does this? Well, the front half of it you can see, and the back half of it you have to see where it goes in the fundamental domain, and it just goes around the back. So the tangential base point is a tangential base point that's here now. And this is this. And you really just have to see where the action of S3 takes this other triangle. It identifies them, right? And what happens to this? And I'm answering your question. It just becomes here, and what you get is a loop around this point. Okay? So it might be a little more complicated than that. But roughly speaking, this is exactly what happens. It's something which is not a loop. How do you know when something which is not a loop up here becomes a loop? Easy. Its two endpoints have to be identified in the quotient, then it's a loop, okay? So you believe me, the 6 base points are identified, so it does become a loop. So this is the braid group, mod center. This is equivalent, these two guys are equivalent. This is the free group on something of order 2 and something of order 3, so it's PSL2 of Z. Okay, so I'm saying the same thing in two different ways. PSL2 of Z, which is more familiar when people are used to quotienting by S3 and having elliptic curves, and the braid group, which is the situation we're going to be looking at now. They're the same group in this case, okay? Now, inside this group, sigma 1, sigma 2, you have sigma 1 squared, sigma 2 squared. So what that means is this loop upstairs and this loop, these two loops. So these are the x and y that we were saying this morning. And it's like we saw the cover. Here you have the quotient. Here you have the universal, the Teichmüller space, universal cover. The whole group is PSL2, and this one is F2, and it's a subgroup of the whole thing, and this is what that subgroup is. It's F2, generated by these. So this is gamma 4. This is gamma 0, 4.
You're saying the subgroup generated by sigma 1 squared and sigma 2 squared is a free group.
Yeah, it's a free group, exactly. Inside this group, it's a free group, and it's F2, and it is exactly the pi 1 of P1 minus 3 points. Okay.
And then why do you see sigma 2 square as the loop which starts from 0 like you did, and not just the loop around the second point?
What you have to do, because that's unfair, because I compose two things which are not loops. So what I'm really saying is sigma 1 squared, I'm looking at it downstairs, and then I'm lifting it back upstairs. It's the only way you can make sense of that. I can't really say sigma 1 times sigma 1 when it's in a groupoid. It's downstairs and it's the image of the loop x, okay? That's what it means anyway. I mean, what does it mean when I say x is in F2, which is a subgroup of this whole pi 1? So it should be a loop down here, really. I'm just saying it's the loop image of the x up here. Okay, so now I've reached the point where I can define G. No, maybe I'll say one more thing. Maybe I'll just do the case n equals 5. I want to tell you who gamma 0, 5 is. So,
What do you mean by gamma 0, 5?
gamma 0, 5 is the pi 1 of M05. And in fact, it's the pure braid group mod. Those two relations, the same ones. Now those two relations that I modded out by are pure. So I mod out the pure braid group Kn, K5 by those two relations, and that's my gamma 0, 5. Okay, but I have to tell you who it is. So it's all pure braid groups actually, for all n, they're generated by the following braids. So I'm picking this set of generators. So you take the I strand and the J strand, and the I strand sneaks around behind everyone, hooks around just this one, and goes back behind everyone. And that generates the entire pure braid group, and there are some rather ugly relations that you don't want to know, which can easily be written down. But there are many relations. So in principle, they're generated by xij for 1 less than or equal to I, less than j, less than or equal to n. You have to take them all. But there are all these relations that mean that actually you can take less. And so in fact, for 5, it's enough to take. There are several different sets of 5 that you could take, but I like to take these, for my purposes now, I want to take these cyclic ones. x5,1 is the same thing as x1,5. I like to write it that way because it looks cyclic. Xij. I define x xji, that way when j is bigger. Okay, and there are some relations here that we don't need to go into in detail, but x12, okay, xij commutes with xkl when ij and kl don't know each other. Again, you can see that right away. If KL is over here, or else if KL is in this group here, they just commute. You can do one first, then bring it downstairs, okay? Let's see the, I don't know which one, 1, 2, 3, 4 maybe. In B4, remember I told you that gamma 0, 5 is in B4 mod center. So I'm going to talk about B4 mod center here, remembering that gamma 0, 5 is contained inside it. Then it's a really easy little computation with the braid relations to see that C minus 1 sigma I C equals sigma I plus 1. This conjugating by this thing to say sigma 1 to sigma 2, sigma 2 to sigma 3 is just, but it takes sigma 4 to something weird because it's of order 5. This is of order 5, right? We saw that the fifth power of that is the center and we're modding out by the center. So it takes sigma 1 to sigma 2 to sigma 3 to sigma 4 to the conjugate of sigma 4 by all this, which is a long thing, and back to sigma 1. Okay, I'm going to use that later. Now I have everything I need. I can define GT, keeping in mind that what's going to be interesting is that GT is going to go and be mapped into automorphism groups of these pi-1s of the moduli spaces. And in fact, this is basically what definition is going to come from. We're only going to need to look at 4 and 5 to give the definition of GT. Now, I don't actually need to use these groups. No, I don't need to use this as a definition of GT. I'm just going to give you the straight definition of GT, and then I'll work on proving that. So now I'm on to part 2. So I can finally tell you who the Grothendieck-Teichmüller group is. So first there's a simpler group, which is GT0. So this group, which is not even that easy to see why it's a group. So let me just say the set. It's a set of pairs. This is in Z hat star, and this is in F2 hat. So there's going to be some properties, but before I say the properties, let me remind you. So F2 hat's the profinite completion of F2, so it's to be really viewed as the profinite pi 1 of P1 minus 3 points. And Z hat star is a Galois group. This is the right way to think about it, of Q abelian, which is Q when you add all roots of unity to Q over Q. Now I have some properties on this pair. So I have 3 properties. So I'm going to write F equals F of xy. This is exactly what we saw this morning. Whenever you have a map from x2 hat to any group, finite, profinite, or whatever, that says x to A and y to B, we write F of AB for the image. And so F of xy is just F, under the identity map. And F of xy, F of yx equals 1. I'm also going to write this as theta of f equals 1, where theta of x equals y and theta of y equals x. This is an automorphism of f2. So this is just another way of writing the exact same thing. Theta just exchanges x and y, and so it's f times theta of f equals 1. F of xy, x to the m, f of zx, z to the m, f of y z, y to the m equals 1, where m is lambda minus 1 over 2. Now this is a profinite number. This is a number in z hat. Lambda is in z hat star. That means lambda is invertible mod every prime. Lambda is invertible mod 2. So when I take lambda minus 1, it makes sense to divide by 2. I can do that. So this is a number in z hat.
And what does it mean to do x to the power of someone in z hat?
Okay, so just let me write x, y, z equals 1. Okay, you have to understand what's meant by a profinite group and what means when you actually take a power in a profinite group. So a profinite group is let's say f2, say, profinite. It's the inverse limit of f2 to the n. So what is an element of this group? What does it mean even if I say x? So any element, let me not write x, any element. What is it? What is it? It's this big tuple of gamma n's in all of these finite groups for every n. And all of these groups are finite, so all of these gamma n's are of finite order. Okay? And I can take an element in z hat. So z hat is the inverse limit of z mod n for all n. Okay? And, okay, if I have an element of z, an integer, then I get an element of this. Just it's the image of z, if it's the image of my integer in, let me not call it. If I have an integer m in z, I certainly get an element like this. And I can just, yeah. But even if I don't have an element in z, even if I just have a coherent tuple like this, okay, I can raise all of these to that power in a coherent way. So that if I've raised it to the power in one of these quotients, and then this quotient maps down to a smaller quotient, my power maps down to that other power. Okay, so when you take the power of an element in a profinite group, you take it to an infinite tuple of integers, one for each thing in the quotient. And that tuple is coherent itself. Otherwise, you wouldn't have that the power was coherent for all the quotients. And what it means for that tuple of powers to be coherent exactly means that that tuple is in Z. But no one ever works with profinite groups that way. This is the kind of thing you want to quickly forget.
So how do you do then? If you technically, what do you do when you forget about that?
Technically, you just say that m is a profinite number, and you have x to the m, and x to the a times x to the b equals x to the a plus b, and it works exactly like powers. Yeah, because it is exactly powers in every finite quotient. And they're all compatible. And that's what we're really doing. Okay. So, before I get rid of this board, I'm going to write omega fx to the m squared, omega fx to the m, fx to the m equals 1, where omega takes x to y, y to z, and z to x. So omega, again, is just an automorphism of f2. It's a sort of 3 automorphism of the free group. Z is just x, y is equals 1. It's actually to be thought of as a loop around infinity, right? And omega just turns the 3 generators. And this is just another way of writing the exact same relation, but I like to write it this way and this way. And the reason I like to write it this way is because they look like cocycles, and they are cocycles. And there are coboundaries associated to them, which is something I may or may not have time to get into. Okay, I have to give you the third relation now. Third relation is by far the most famous relation, the most wonderful relation, and it's related to all kinds of wonderful math. It's the pentagon relation, but it doesn't live in F2. So those other two relations live in F2, but this one doesn't. Oh, it's f of x1, 2, x2, 3, x3, 4, x4, 5, x5, 1, x1, 2, 3, 4, 4, 5, 1, 2, 3, 4, 5, 1, 1, 2 equals 1. So in gamma 0, 5. So these are braids in a braid group. They're the braids that I drew up there.
So you have defined omega on generators, and you extend as morphism of groups? Or?
Omega is to be seen as an automorphism of F2.
Okay.
Theta and omega are in aught.
Okay.
F2, discrete, or profinite, both. They're just automorphisms of this group. Okay, now I have an automorphism of this group as well. I'm going to call it rho. I have an automorphism rho, and it's given by conjugating by C. It's given by this, except I take rho equals in C squared. It's more convenient to take the square. So all of the indices advance.
What do you mean by in?
In. It's the inner automorphism.
Okay.
This is in here. And gamma 0, 5 is in here. And the inner automorphism by this well, gamma 0, 5 is characteristic. And it's the kernel of of the surjection onto permutations, and if I conjugate something like that by anything, I'll still have a trivial permutation, right? If I conjugate a braid,
So can you repeat?
if I have a braid that's pure, in the sense that the ends of the braid stay where they were, and I conjugate this braid by a braid that isn't pure, the end result will still be pure. So this is preserved under inner automorphism even by non-pure braids. And so when I conjugate by C, I preserve this group. It's an automorphism. It's inner in the big one, but it isn't an inner automorphism of gamma 0C, of 0,5. It's to be seen as an inner automorphism inside here, but it isn't an inner automorphism of that. It's an automorphism. And it just cycles around these 5 generators. So I'm using it, it's convenient to use it twice, to use the square. So I can write this as rho of F, rho squared, rho F equals 1. Another co-cycle relation in here, okay? Okay, now, there are 3 things left that I would like to say, and I won't have time to prove them. So the first thing I want to say is, for lambda F satisfies just relations 1 and 2. Let me look at them. If and only if sigma 1 goes to sigma 1 to the lambda, and sigma 2 goes to F sigma 1 squared, sigma 2 squared inverse. Sigma 2 to the lambda, F sigma 1 squared, sigma 2 squared. Remember that sigma 1 squared, sigma 2 squared, if you think of all this geometrically, and this is being the pi one, this is x and y, the loops around 0 and 1, is an extends to an automorphism of B3 mod center. That is actually literally the meaning of this relation 1 and 2. All it means is, well, I showed you how to define this group by 2 relations. One of the relations was this. The other relation was this. Squared. So if I want this thing to extend to an automorphism, I have to check it on those 2 relations. So I'm not going to do the proof here because I don't really have time, but I'm going to tell you how the proof goes. It's just a boring calculation. You calculate what it does to this, if it is an automorphism. So sigma 1, sigma 2, you calculate where it goes, and it goes to sigma 1 lambda, F sigma 1 squared, sigma 2 squared minus 1, sigma 2 lambda, F of sigma 1 squared, sigma 2 squared. And it looks horrible and you're upset, but it's not horrible because what you do is you take 1 factor of sigma 2 over here to the left. So you write this, sigma 1 to the 2m, sigma 1, because lambda is 2m plus 1, right? So the lambda becomes 2m plus 1. Sigma 2, and inside here, I'm going to conjugate by that sigma 2, because if I'm conjugating the whole thing by sigma 2, if I'm conjugating all of this by sigma 2, I'm conjugating each argument. So I conjugate this by sigma 2 and that by sigma 2. I'm not going to do the whole calculation because it's easy and boring. Here I'm left with 2m, and here I'm left with the thing I had before. And now, if you compare this to my relation 2 over here, you see that it's half of this relation here. This is like an f of z x z to the m, well, I'm not doing it very well, but f of x y, this thing here. And because I have relation 2, I can change it to a relation where, apart from the m terms are boring, I get just 1f. And roughly speaking, I get sigma 1, sigma 2 goes to itself times, I'm not being very precise, I don't have time, but I've left out all the m's. But roughly it's something like this. And then this is just a consequence of relation 2. It's made for it. It's exactly the relation that means, of course I've left out all the m's so you can't see them, but relation 2 is exactly what means that this action respects that relation. And similarly, relation 1 is exactly what makes this one hold. So 1 and 2 are equivalent to lambda f being an automorphism of this group. And what that means is that GT0, this is the pairs with just relations 1 and 2, is a group. We just proved that it's a group. I'm going to talk about its multiplication. It's a group if you identify every pair as an automorphism and compose automorphisms. That's the group law. So let me write down what that means explicitly.
There is a theorem behind that. You say that any pair is an automorphism. You can compose them, but then the composite has to be of that shape.
This is because it's if and only if. If you have an automorphism of B3 mod Z that does this to the generators, it satisfies 1 and 2. So you compose them, you know it's still an automorphism, you check obviously that it still does this to the generators, and so it satisfies 1 and 2. So it's an if and only if. I could prove it all in detail, but we'd be here for another hour. And it's really not, it's direct. You know, if there was something tricky, I would tell you, but there isn't. I got really good at these calculations at a certain point. Pages and pages
But
of
if you
that.
compose two of them, it's a power on the left and it's a conjugation by F and G.
Yeah, exactly. And since you have an if and only if, you know it then satisfies 1 and 2. Okay, so what does it actually mean to multiply two of these things? You have to compose the automorphism. So let me write that this is an automorphism. You only have to, you'd have to do it on F2. F2, I'm identifying F2 as sigma 1 squared and sigma 2 squared. That's the right geometric identification. So this is sigma 1 squared, so it just does this. And this is sigma 2 squared, so it just does this. And this is an automorphism as well as being a pair. And the product is lambda mu f times f of g. That's just what happens if you compose the two automorphisms. Now I'm going to apply, let me compose something the other way. Let me do lambda f first, and then mu g. So I've done lambda f here. I've done it. This is my automorphism. And now I do g of that. And what do I get? Well, this goes to x to the lambda all to the mu. And this goes to f of something ugly, y to the lambda mu, f of something ugly, times g. I'm not doing it right. F of something ugly, which are the images of g. G of xy inverse y to the lambda mu, g of xy. F of something ugly and something ugly.
You are applying G, so you are conjugating by G.
I first did F. No. I'm just applying G. I first applied F, and I got this. I'm applying big G. I'm applying the automorphism big G, which conjugates sigma 2 by little g.
Yes, but if we look at the formula, it means that you...
So here I've applied big F, and it conjugates, right? Now I'm applying big G
to this.
To this.
At the extreme,
So I apply big G to this. I won't write it down. I'll just do this. Okay. Minus 1. Then I apply big G to y, and I get this. And then I apply big G to this. So it's G of F. So the formula I had before was right? What am I conjugating y by now? I'm conjugating it by all this. And this is the multiplication in GT. This is the multiplication. But it really is to be thought of as just composing automorphisms. It's in the multiplication in GT as well. Let me just say the same exact thing for GT.
But so far we have no definition.
So far, GT is the one with 1, 2, and 3.
We call it GT0 there.
Oh, sorry. Yeah, GT0 is living on this board. Okay. Sorry. Okay.
No, but then what is GT0 without the half?
GT equals lambda x in GT0 with also this. Okay.
What about the hat? I mean,
They all have hats. Everybody always has a hat.
everybody has
Always
that.
has.
Okay.
Everybody has hats. And now I can tell you that they are profinite groups, finally. Okay.
Also, I'm sorry.
They all have hats. GT0 has 1 and 2. GT has all 3. Okay.
They all have hats.
Now I can tell you, so now we know that GT0 is a group, and we also know it's a profinite group because we saw that this morning. Because an automorphism group of a profinite group is profinite, you take its finite images in all the finite quotients of the group it's acting on, and it's the inverse limit of that. So GT0 is now a profinite group, and now I'm going to say the exact same thing for GT. I'm going to say everything that I just said, except that 4 will become 5. GT,
I'm sorry, in GT naught there is no relation or are there relation? I'm confused.
GT naught is 1 and 2.
In GT,
GT is not is with 1 and 2. It's what's on the board over
only
there.
1 and 2.
1 and 2.
And you impose one more.
You put one more. But the pentagon, I mean, it's the one you like. So, okay? Okay. So here you have a lemma that's almost exactly like the one I had there. In fact, lambda f if you just decide that it's going to act on, it's a little more convenient to do what I'm about to do. I'm going to extend the action to B4 mod Z, remembering that this group is inside there. So I'm going to set C squared goes to F x23 x12 C squared, and sigma 1 goes to sigma 1 to the lambda. Now, this group is generated by these guys, because I told you that C, as it conjugates sigma 1, it sends it to sigma 2, sigma 3, sigma 4. You get them all. From these two generators, you get the whole group. So I've given a candidate automorphism for the whole group, just on these two generators. So
C was the product of all the sigma 1, sigma 2, etc.
yeah, C. I take the square again just for convenience. If I don't take the square, I have 2 F's here. It's a little uglier, but of course you could do that too. Okay, so I propose an action of lambda F on the generators of B4 by this, and I have the same lemma as before. So this action.
I have a question. For this C, because you told us that it's in B4,
Yeah,
not by the center, but before there's just 3 strands.
oh,
For full strands.
4 strands and 3 generators.
no, you're right.
Generators and 4 strands. Yes.
Yes,
So
it's
why
generated.
is there a sigma 4?
You're right. Let me put it, you're perfectly right, sorry. So let me just use B5 and not quotient by the center. And quotient by the center and the other relation. Okay. I'm going to identify gamma 05 with the pure subgroup of this, which is gamma 05. Otherwise, I can't have that element. That's very true. Okay. So this action, just given on the generators, extends to an automorphism of, in fact, it even works on B5, but I can stay with the quotient. If and only if lambda f is in GT, which means that I have these relations. I already need 1 and 2, and I also need relation 3. Relation 3 comes from just the fact that this element here is of order 5. When I take it to the 5th power, and I have to take its image to the 5th power, I get something like f x23 x12 c squared, and the same thing. But C, when I conjugate by C, it just shifts the indices of these. And if I move all the C's to the left, I just shift the indices each time, and I get the pentagon.
Can you repeat?
I'll write it. Let me write this out. The pentagon means that the relation C squared to the 5th equals 1. C to the 5th is the center of this group. If C is of order 5, then C squared is also of order 5. It's really just convenience to use C squared. So I have this relation. So if I want to have an automorphism, I really had better have that this is order 5 too. So I take it to the 5th power.
Because this is the image by the automorphism of C squared.
I'm saying that the pentagon is equivalent to this being an automorphism. So one thing is very simple. If this is an automorphism, I definitely have to have the pentagon, and I'm showing you why. The other is more complicated. You have to work. But it's not that complicated. It's just work. Okay, but let me just show you why if it's an automorphism, you need the pentagon, because this is where the pentagon comes from. It comes from just the fact that the 5 cycle is of order 5. Well, okay, so I write this out 5 times, okay? This has to be equal to 1. And now, what does it mean to conjugate by C? I bring all the C's to the left, all of them, okay? And here I have C. Well, let me just do the first one. Let me bring the C's to the right, because there's already a C squared on the right at the end. So just look at this particular term. This is the end of my... This is the end of it. Now, I'm going to do this. I'm going to write C fourth, C minus 2. Now I'm going to just bring this C squared and this C minus 2 in here. Okay? But C just shifts the indices. We saw that conjugating by C takes sigma 1 to sigma 2, sigma 2 to sigma 3. It takes x1, 2 to x2, 3, and so forth. Conjugating by C squared moves them 2 places. So I get I just shifted them by 2 places. 2, 3 gets pulled back, 1, 2, 5, 1. 1, 2 gets pulled back, 5, 1, 4, 5. Okay? And now I have a C squared here, and I make that pass to the right, and again I shift all the indices, and I just do it with all of them, and I end up with the pentagon, and that's where the pentagon comes from. So I've just proved to you that if this is an automorphism, you must have relation 3. The other way is a bit more complicated, but it works also. If you have relation 3, then you get an automorphism of this group. And so now I've proved to you I haven't proved, but I've told you that GT is a group because you're identifying it with an automorphism group that acts this way on the generators. It's a profinite group because its automorphism is a profinite group. And its multiplication is composition of these automorphisms, which is exactly the same expression as we had before. Now I can finally get to GQ, because now I have to compare GT with GQ. So before, this morning, we saw that if you have an element of GQ, you can associate to it chi of sigma, which is the cyclotomic character, and it ends up in the Galois group of Q abelian over Q, which is just this, and an F sigma. And the way we did that this morning was this path P, which is just the path from 0 to 1, is sent to P precomposed with a profinite loop. So a profinite loop is an element of the profinite completion of the pi1. But it works the same way as the pi1. I mean, it's just an all finite covers at the same time in a compatible way. If these endpoints are preserved, are defined over Q, then the GQ action on this groupoid is going to fix the endpoints of the path. So it will map the path to some loop, profinite loop based at this endpoint, followed by the path. But there's a simpler way we could have said the same thing this morning, which was x goes to x to the lambda, and y goes to f minus 1, y to the lambda, f of xy. We know that GQ, or this is f sigma, we know that GQ does this because of all the theory of this morning, right? This is the main thing that we have to retain from what was going on this morning. The GQ acts on this fundamental group, preserving inertia. Because it preserves inertia, that means x, y, and z are all going to be raised to a power n conjugated. I'm only interested in x and y because I'm only interested in what it does to the generators. So I can lift it to an actual automorphism, and since it's up to inners, I can make it that x is not conjugated.
Again?
I want to lift this to an actual automorphism. So it conjugates x and raises it to a power, it conjugates y and raises it to a power. But since I'm working up to inner automorphisms, I take away the conjugation of x. There is a lifting to an actual automorphism that looks like this. This is chi of sigma, because I'm only talking about the Galois group right now. Okay? Now this is not completely well defined because I could multiply it on the left by a power of y, and you wouldn't see that in this automorphism. And I could multiply it on the right by a power of x, and you wouldn't see that either in this automorphism because it would still be not conjugating here. So if I change this f sigma here by a power of y on the left and a power of x on the right, I would have the same automorphism. what I do is I fix the choice of f of xy by asking for it to live in the derived subgroup of f2. If I require it to live in the derived subgroup of f2, then there's a unique choice here. Because if I go multiplying it on the left by a y and on the right by an x, it won't be in the derived subgroup anymore. The derived subgroup is the kernel of the two maps sending y to 1. This is a multiplicative cyclic group, if you don't mind. Well, it's a multiplicative cyclic group, and x to 1. The derived subgroup can be identified with all elements that are in the kernel of the intersection of these two kernels, which means that the global power of x over your whole word, if you ignore y, is 0. The global power of y over your whole word is 0. So if I have something that's in the derived subgroup, I cannot multiply by a power of x and a power of y. This is it, it's unique. And this fixes this uniquely. And it's the same f that comes here. And that's very easy to see because y is just p followed by theta of x followed by p minus 1. And sigma commutes with theta. So first it does its p. Then the theta of x becomes theta of x to the lambda, because sigma commutes with theta. Theta is just 1 minus z is defined over q. We saw that this morning. And then here you have f sigma minus 1 p minus 1. And that is just, this is just y to the lambda. This here is just y to the lambda. So the f I'm giving here is the exact same f that's being given here. And you didn't actually need to have a groupoid and tangential base points to express it. I just expressed it more simply by saying, once you know this, you can lift it this, and you can choose your f sigma uniquely, and this is how you get an f sigma associated to GQ in a slightly simpler way. Okay, so now you really would like to know why GQ is in GT, and this is the last thing I'm going to do. And I'm going to give you a really simple reason, and then a more complex but reason that makes you understand better. The really simple reason is this. GT can be identified with an automorphism group of this. This is not completely true what I'm saying. You need to add one little condition to prove this isomorphism. There's an outer automorphism group of gamma 0, 5, which is obtained by permuting the marked points, and it's Sn. You can realize Sn is outer automorphisms of this group. And because Sn is defined over Q, GQ commutes with this.
It's 5 in this case, no?
5, sorry. Okay.
So sorry, but here, what have the conclusion of what you've shown just before is that GQ is where?
Oh, this is, no, I haven't shown this yet. I'm going to show it to you now. This is theorem. The conclusion of what I said before is that I have a simpler way of telling you who is the f sigma associated to a sigma. You don't need to have the tangential base points and the groupoid in the path from 0 to 1. You just need to use this, and then you lift it to an automorphism of this form, and you choose the unique one that's in the derived subgroup, and that's your f sigma. So that's what I was saying. This is a simple way of saying there's a unique element in f2 hat associated to an element of GQ. Now I'm going to use that to tell you why this is true. And I'm going to tell you in two different ways, the simple way and the complicated but more revealing way. The very simple way says, once you have this isomorphism, so I almost proved it before. I mean, I identified GT with the automorphism group of something very close. Now you have to work a little bit more to show that it's exactly equal to the ones that commute with S5. But it's something that's, it's straightforward. But of course, GQ does this. GQ is an outer automorphism of this group because this is pi 1 of moduli space. And GQ acts on pi 1. It's got a star because it's inertia preserving. GQ is always inertia preserving. And it commutes with S5 because this S5 action is defined over Q. So GQ does this. So GQ is in here. Okay, so that's the simple reasoning. But that doesn't answer the question, direct question about why. How can you see that these satisfy relations 1, 2, and 3, those relations that you actually have? And now I'm going to show you, this is the end of my talk, pretty much. I'm going to show you a very cute trick that's useful for two different things. It's useful to understand GT better and to understand why the F sigma defined that way satisfies the relation.
Sorry, so did you also prove that the map is injective?
I did put that the map is injective. It's really an inclusion. I mean, GQ is a subgroup of this group, right? Now, yeah, that's actually okay. That's a legitimately good question, and you have to show that this is an injection. I will talk about that at 4. At 4? Wow, that's really soon. That's a consequence of Bieli's theorem, actually. If the pi1 is sufficiently complicated, it will always be injective. It only isn't injective if the pi1 is too simple. This one is really sufficiently complicated, and I will actually prove that this afternoon. I'll talk a little bit about this on also. Okay, I want to say my last thing. So my last thing is, why does F sigma satisfy relation 1? I'm only going to do relation 1 because 2 and 3 are more complicated versions of the exact same reasoning. So if you've seen this one, you've seen them all. Okay. So I'm going to let theta of z equal 1 minus z. And theta of x equals y, and theta of y equals x. This is an automorphism of F2. This is acting on P1. But they're related, these two things. And I'm going to say, we know that if you have any rational point and a path going between two rational points, Galois will act on it, sending it to another path going between the same two rational points. These are profinite paths. And I'm going to use the point 1/2. And I'm going to take this and call it R. So I have P is R followed by theta of R inverse. Because R goes this way and theta of R goes that way. And if I switch it, I just get P. And I know that sigma acts on R by sending it to some R G sigma. Because it will fix these two base points for the same reason. 1/2 is defined over Q. So we'll precompose it with a loop and then do R. And so, now I'll do a Q calculation. Sigma of P is P F sigma. But it's also theta of R minus 1 R. Well, it's also sigma of theta of R minus 1 R. Sigma commutes with theta. Theta is 1 minus z. It's defined over Q. So this is theta of sigma of R minus 1 sigma of R. So this is theta of R G inverse. So G inverse R inverse. RG. So this is theta of G minus 1, theta of R minus 1 RG. Almost done. Which is theta of, I'm going to write G of xy. G is G of xy. It's in f of xy the same way I did before. Theta of R minus 1R is P. So I'm back to P here. And this is G of xy. So this is theta is G of. Okay, now what is theta? It's G of theta of x, theta of y. So what is that? This is x, and this is theta of x. So theta of x is equal to P minus 1. Theta of x is this. So it's equal to, let's see, it's P, how do I do this one? Theta of y is this. That's P minus 1 xp. P minus 1 yp. So if I did it right, so I write P out here and a P minus 1 here, PP minus 1 on the left, and then this conjugation, I'll bring the P inside. And I get yx, simply yx. Which is another way of writing theta of g, but theta is now the group automorphism that exchanges x and y, g. So I've said that P maps to PF, but it also maps to P times this.
Why did the P disappear in the middle?
I conjugated. I put
Okay,
P minus 1 there, and I brought them inside. Okay?
Calculation says that theta P is P multiplied by these two factors. That's what you say? No.
The calculation shows that P, sigma of P is PS, but it's also P times this. And so F is equal to this. This is just theta of G, but now theta is not 1 minus Z. Now theta is the group action that exchanges X and Y. It's a little theta. So this is just theta of G minus 1G. So, of course, theta of FF equals 1. This is F sigma. This is all sigmas. They're all sigmas all the time. Right? It's a co-boundary, and this is a co-cycle condition. This is trivial now. Sorry. This is relation 1 that we wanted to prove that F sigma satisfies. But of course it satisfies because it looks like this. It's a co-cycle. It's actually co-boundary. Okay, so if I tell you that you can prove that F sigma satisfies relations 2 and 3 exactly the same way, simply using a different path. To prove relation 2, you take your 6th root of unity and you use a path S that goes to there. And you do the same calculation, and you find that F sigma, it isn't exactly a co-boundary. It can be either a co-boundary or a co-cycle with something extra, but it has a form similar to that. And therefore, it satisfies relation 2 in an obvious way. And relation 3 is the same, only you can't do it on P1 minus 3 points. For relation 3, it's not surprising that you have to move to M05 and take a very nice path on M05, which is a boundary of the associahedra and has everything to do with operads, I guess. But maybe we'll have time to talk more about this next time. There's a certain path on the moduli M05 which will play the exact same role, and it will give you the fact that F sigma satisfies relation 3. But really, when you've seen one, you've seen the essential reasoning. Okay, so the last thing I can say is that when we saw that, our first thought was, but GQ does more than GT. GQ isn't just satisfying these co-cycle relations 1, 2, and 3. It's co-boundaries. So maybe it's different from GT. Maybe this is the proof that they're not equal. So does GT satisfy that? Does there exist a G such that F equals theta of G minus 1G for all lambda F in GT? And the answer turned out to be yes. And for the other two relations too, obviously. Okay, there's a very, very nice non-commutative cohomology theory that gives you the fact that all F's in GT satisfy not just the co-cycle defining relations, but actual they have co-boundary shapes. I keep saying co-boundary, but it's not completely true.
But here G depends on F. Or
There's a G, simply, which lives in F2 hat. It exists. Such that, and theta is the thing just exchanging X and Y, such that F does have this form for all F in GT and not just for the ones in GQ. So pretty much I'm finished for today. I think I've hopefully convinced you that GQ has lots of really good geometric-based reasons for being in GT. Okay, so what I want to get across is what the group GT is, the fact where it comes from geometrically, that it comes from acting on these moduli spaces of the pi ones of moduli spaces, and that GQ is inside it for deep geometric reasons. That the question, okay, I didn't deal with the injection, I will later this afternoon, but the question of surjection is, I guess, the biggest main open question of Grothendieck-Teichmüller theory. We're going to have other versions of this, maybe going into higher genus, and also the versions which are pro-L, the other completions, pro-unipotent, Lie algebra. You can ask many, many versions of this question, but it remains the central question. Okay, and what I didn't talk about at all is the two-level theory, but I guess I don't have time to do it now, so it will come out next week. Yes.
you say again what you wanted to say with this last line? Does there exist a G such that blah blah blah? You say yes, there exists one.
Yes,
Or
for all lambdas f and gt. I only showed it to you for the Galois group. I showed it to you for the Galois group, and I used the fact that the Galois group acts on a path from 0 to 1/2. That's Galois theory. We don't have anything like that for GT. We don't have any arithmetic for GT. So we weren't able to use these methods. GT acts on a path, etc. So we had to use completely different methods to prove this. Methods of cohomology, methods where you have to calculate a non-commutative cohomology. This is the module that's being acted on, but it's not commutative. This is the thing that's acting. It's the order 2 group of that automorphism theta. And you want to the cocycle relation theta FF, that's a cocycle in this cohomology group. And what you can prove is, using a basic theory of Serre that tells you in nice enough cases, like a free group, how to calculate this cohomology group, you see that it's trivial and that there are only co-boundaries, okay? So that's how you do it in a general case.
and if it was not possible to find such a G, you would conclude that this is not surjective?
You would conclude that GQ is different from GT, of course. Of course.
That's a good point on this question.
Yeah.
And so there's no...
If you could find anything that GQ does that you know GT doesn't do, you would be done. But everything we've ever tried that GQ does, either GT does it or you don't know, we can't prove it. So we still don't know. Yeah, there was many years were spent by lots of people running after a new thing that GQ does. Oh boy, does GT do it. It's still happening. And I mean, either we don't know or people prove that it does it. With harder and harder proofs like that are getting really difficult.
So what is the conjecture? People would conjecture that they're the same or they're different?
Nobody wants to conjecture that they're the same. Nobody wants to formally conjecture,
Yeah.
de point, they are
Yeah.
the same. But there have been lots of people, I think that Cartier, for instance, he has some good ideas about GT is the, he left about a minute ago, just a minute ago, like, just when I was on to wait. I think he's very punctual, it's 3:30.
Okay.
GT is the pro-algebraic envelope something something. GT pro unipotent is the fundamental group of the Tanakian category of representations of GQ.
Okay.
GT is the something you get from doing something with GQ, so weaker conjectures. I don't know, myself I've been back and forth over the years, I just don't know what I think. Actually, I think not. But that's because we had another relation to make this act on the moduli spaces in all of higher genus. So I think that's the right group. But it doesn't make much difference. It's still kind of yes.
Can you rewrite the relations in terms of G?
Well, no, the relations become trivial. This becomes a defining condition that replaces relation 1.
But
Relation one's-
what about 2 and 3?
Yeah, the same. I can tell you pretty much. I mean, I left out the M. There's some M's in here sometimes. But, G, you need H. You need something like, well, okay. Ignoring the M's, when you take the case lambda equals 1, it's just this.
It's not the same G, right?
No! No, I don't think so, and I have no idea. Actually, I don't know if that's false either. Now that you ask, God, I really don't know. And it's the same. I'm not being completely honest, but you're allowed to put a little thing here. But it's the same here. This one is quite interesting, because K is in gamma 0, 5. But this, it's not really in gamma 0, 5. When you look at F, yeah, it's F of x1, 2, x2, 3. It is in gamma 0, 5, but it's just one little piece of gamma 0, 5. So it's a lot harder to look for these. These you can completely classify them. But these, elements of gamma 0, 5, such that when you do this, you get something in a little subgroup, suddenly becomes much harder, sadly, to really work out. But they're fun things to play with.
What time do we resume?
You're the master. You choose.
Or 15, let's say. But I won't be an hour and a half on it.
No.